Okay, so we're back to permutations. Okay, now again, if you're using the old textbook, which maybe even data management students from day school will be using, then it won't be section 3.1, it'll be section 4.3. Okay, the other thing that when I do this little demo here, and to explain why it is that we do what we do when we have elements that are the same as each other, we have a problem. And the problem is that this should be in color. Okay, so what I do is I have a good copy version of this that's doodled all over. Okay, but first I want to explain the idea. Okay, so far when we've had four-letter words or done arrangements, permutations, okay, where we have specific elements in different positions, all of those elements have been different or unique, which means that they're exactly the different letters. Okay, 12 assorted jelly donuts, different letters, different colored flags, all kinds of different people lining up for photos, stuff like that. So this would be an example of where we would have, I don't know, identical twins lining up for a photo, or an example of where we'd have be arranging letters where there's two letters that are the same, or we'd be, eating jelly donuts, but some of those jelly donuts would be, repeats. There'd be 2 chocolate dips or 3 jelly donuts or whatever. Okay? Because, of course, in this situation, what we have to do is we have to remove some possibilities because they'll be identical to each other because we have identical elements or elements that are different, that are the same rather than different from each other. If they're different, they look different. They're different arrangements. But if they're the same, they don't look the same. Sorry, they don't look different, and as a result, they're actually, we count them as being different, but then we have to remove the difference that we gave them, and that's the strategy that we're going to use. So we'll get to that in a second. Okay, so in this situation, you'll notice the letters that we're going to arrange, and that's what it is. How many different ways can you permute or arrange the letters in these words? And I'm going to use Abby. In this case, Abby, there's 2 B's that are identical to each other. Now, I do a situation of where they're identical to each other. Okay, and I do a situation where there are different colors. Okay, and that's when you're like, well, I don't see any different colors. That's when I have to introduce the one that we've doodled all over. Okay, again, these are your perfect notes that you should be following along as we're doing things. Okay, and what you'll notice here is I've got A, B, B, Y, but the 2 B's are different because one B is red and the other B is black. So what I've done is I've done all these arrangements, and we know the way that this works, right? We've got 4 elements in 4 positions. We're arranging all those letters to form 4-letter words. And so I've actually listed all of the different outcomes, but you don't have to. You would just do 4, you would just go, 1, 2, 3, 4 spots. Okay, you have 4 elements, then 3, then 2, then 1. There's no restrictions. Okay, or you could just go 4P4. Okay, and you get 24. And that's the way that it works. But in this scenario here, and I'll probably include this, okay, because this is what it actually looks like, and I've crossed a bunch of stuff out. Okay, in this scenario, you'll notice that the B and the B are both the same, BB. Okay, so as a result of that, I do all of these same arrangements as if the 2 B's are different. So I list them all as if they're different, and all I did is copied and pasted this in Microsoft Word, and then I just changed all the B's back to being black, so they're both black and both identical to each other. Okay, but what you'll find out is that we have ABBY and ABBY there. Okay, and that doesn't work. Okay, because they're exactly the same. So I can't make that a different arrangement. If I'm asking how many different arrangements there are, you can't repeat yourself twice. It doesn't make any sense. And this ABYB, where's the ABYB? ABYB is a repeat as well. And this AYBB, you can see side by side, is a repeat. Then you've got baby, and then baby repeats. And then you've got BAYB and BAYB, that repeats. And anyway, so there's a lot of repeats. And if you follow through and you see all these repeats that are here, okay, and again, you've got YAB and YAB, that one's okay. YABAB and YABAB. And then Yiba and Yiba, so we've got to cross out one of those. And what you'll find out is, when I look at all the crossouts that I have, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so rather than having 24, it's gone down to 12. Okay, it's basically halved the number of situations. And that kind of, at least kind of rings true in that the 2 B's, there's 2 B's, and we take all the arrangements that would be there if they were different, and we divide it by 2. Hey, that could be a trick. That could be the way that we do this. So what I do then, of course, is I create a scenario where we have 3 identical letters. So I've got the word boo, okay? And in boo, again, this is where I need the color, okay? So I'll go back down to the color. Okay, give me a second here. I'm just going to fold this sheet of paper so we have something to compare it to. But anyway, you've got boo, and so what you'll see is I've got B, and then I've got a red O and a green O and a black O. Okay, and so when I arrange, and here I made a boo-boo, literally, this should be green. Okay, and that should be green. Okay, and that's a little boo-boo. Anyway, bad dad joke. So in that case, we've got boo, and that would be a different arrangement of that different arrangement, and so on and so on. And so there's 24 arrangements, same. 4 different elements, 1, 2, 3, 4 elements in 4 positions. Okay, and we would go 4 times 3 times 2 times 1, or 4p4, and we get the same 24. That's exactly what we're supposed to say, because that's what it would be if they were all different. Same as Abby. Okay, treat them all different. It's the same thing. They're different letters, but it's the same number of arrangements. Now what we do is when we treat them all as if they're identical, and that's what we have in this scenario here. And in this scenario here, okay, in this scenario here, then we've got B and then 3 O's that are exactly the same to each other. Okay? And so what you'll find out is, well, you've got boo, and then you've got all of these that are all repeats. And then you've got O-boo, and that O-boo's a repeat, and that O-boo's a repeat, and that O-boo's a repeat, and that O-boo's a repeat. So anyway, we've got O-boo, that's a unique arrangement, and then we've got U-bo, and then that's a unique, or a different. They're all the same. And then we've got oob. And the rest are identical elements. So what we end up having is simply counted 4 arrangements. So we go from 24, which is what we would do when they are all different, back up here, to 4. Now, it would be nice, we have 3 repeated elements, 3 identical elements. It would be nice if we just divided by 3. Okay, but we don't divide by 3. 24 divided by 3 is not 4. 24 divided by 3 is 8. So where do the 3 and the 2 play a role? Well, if we go back to this situation here with the Abbeys and we divide by 24, we take 24 and we divide by 2, we get 12. Okay, but really what it is if these two B's are different, then we don't just lose 2 arrangements. We lose 2 factorial arrangements. Now 2 and 2 factorial are 2. But if we look here, okay, we take the 4p4 or the 24 and we divide by 6. If we divide by 6, 6 is actually 3 factorial. Well, that's where we have 3 repeated elements and we lose 3 factorial arrangements, because if these were different, let's say they were A, B, C, right? Then we would go A, B, C, A, C, B, B, C, A, B, A, C, C, A, B, C, B, A. So if there's 3 elements that go from being different to being the same, then we're going to lose all of these arrangements that could exist along with the B wherever it is in this scenario. The B could be anywhere along here, or the unique letter could be anywhere along here. So what ends up happening is rather than dividing by 3 for the 3 arrangements, we lose the 3 factorial arrangements. Okay, and so that is sort of a correction factor that we do in these scenarios. That's kind of a good way to think about it, as a correction factor. Okay, so the nice thing about this is we treat it exactly the same. So there's not any real huge new learning. All there is we treat it and ignore the fact that those elements are the same, and then we divide out the possibilities where they are the same. So it's basically a correction factor, and that's why it's great to teach this after permutations, because it lets us practice how to do all our permutations work, and of course help us by eliminating these situations where things are identical. Okay, so let me show you a couple of questions to show you how that works. The general overall formula is the number of permutations of a set of n objects in n positions, so an npn scenario. Okay, I've got 10 elements in 10 positions. Okay, if I have identical elements amongst those 10 elements, let's say I had a dozen donuts, right? 12 elements in 12 positions, because I'm going to eat all 12, or they're going to be arranged in a box or something, or given to different people, whatever it may be. Then what ends up happening is that, let's say of those 12 dozen that I have some unique donuts, but I also have 2 jelly, and I have 3, I don't know, chocolate dip, and I have, I don't know, 4, I can't think of it, chocolate glazed, I don't know, I can't think of donuts right now. So I've got 2 and 3 and 4. That means that's a total of 9. I have 3 other donuts that are different. A sprinkle one, I don't know, a cruller and a apple fritter. I don't know. Whatever. Who cares? Doesn't make a difference. But in that dozen that I have these repeated elements. So what I would do is I would take that 12 factorial and then it would treat them as if they were different, all different. 12 dozen, they're all different. And then what I do is I divide out, I take care of the variability that I lose from the jelly donuts by dividing by 2 factorial. I take care of the chocolate dip by being the same, okay? And then I take care of the 4 chocolate glazed being the same by dividing by those numbers factorial. And that's where this formula comes from. So here's some examples, all right? And I use small numbers just to make the calculations easier. Okay, so how many different permutations are there with the letters in the following words? Okay, and here's Loyola. Okay, and Loyola, what you'll notice is I have 1, 2, 3, 4, 5, 6 letters. So it's 6 elements in 6 positions. Okay, and so my number would be, and you can map them all out if you want to and do 6, 5, 4, 3, 2, 1. Or if you want to do 6p6, that's okay. Or 6 factorial. Hopefully we're there where we can do it a little bit more quickly. But what we do is we have to correct things. We always check. Now, if all of these letters were different from each other, then the answer would be 6 factorial, 6p6. But we've got 2 L's and we've got 2 O's. So I go divide by 2 for 2 L's and divide by 2 for 2 O's. Are there any other repeats? No, there's Y and A. And 2 O's, 2 O's. Yes, so divide by 2, divide by 2. So that ends up being 6 factorial, which is, I think, 720. Divided by 2, and that 2 factorial is 2, 2 factorial is 2, or 2 times 1, 2 times 1. So that ends up being 360, 180 arrangements. Okay, nice closing statement. Therefore, there are 180 different. And that's what we're always going for. We don't usually say different arrangements, but that's what we're going for. Different arrangements. Okay, so that's that little that's all it is. It's a little correction factor, nothing crazy. So to take another example, bookkeeper, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements, 10 positions, because we're repositioning those letters. So it would normally be 10p10, or it would be 10 factorial. But, of course, we have to have correction factor for identical elements. Okay, we've only got 1 B, we've got 2 O's, so I divide by 2 factorial. We've got 2 K's, so I divide by 2 factorial again. And we've got, 3 E's, so we divide by 3 factorial. Okay, and if we had, 4 or something else, whatever. Of course, obviously, we're running out of letters. Okay, so that's 10 factorial, which I believe, I can't remember that off the top of my head. It's 10 factorial. You get used to these, but I'm not as young as I used to be. I don't always remember these. Oh, yeah, so 3,628,800. And then I divide by 2 factorial, which is just 2. And then I divide by another 2 factorial, which is just 2. And then I divide by 3 factorial, which is the number 6. Those are ones that you'll probably get to know pretty well. And so the final answer is 151,200 different arrangements. So therefore, there are 151,200 arrangements of letters in bookkeeper. Okay, now I know that's really messy. Okay, I've got nice, beautiful. Again, you've got your notes. You should be following along with your notes, so you should be seeing this. Okay, these again are the explanations, or this is the companion for the notes. Now we get to candy. Okay, Mr. Henley is eating some M&Ms. How many different ways can I eat them? One at a time. If I was just taking handfuls, it's a little different, but one at a time. Or if you pour them out of the bag, one at a time, or you take them out one at a time like I eat them at the movie theaters. Okay, how many different ways could I eat them? And this is one of those little mini bags. So we've got 4, 5, 6, 7, 8, 9, 10 elements. Doesn't have to be 10 elements. Okay, it just so happens that all my examples I picked 10. I don't know why. All right, 10 elements and 10 positions. So my answer would be that there would be 10 factorial ways to do that. Or if you want, 10p10. Okay? And then what I do is I correct. Okay? For the 4 yellow, assuming that they're exactly the same, and they generally tend to be, that would be 4 factorial arrangements that I would be able to remove. Okay? Because it's a lot of identical. Now, you could put a 1 factorial in here. 1 factorial is just 1. For the 1 blue, In which case, every single permutation question that you've done, you've always been dividing by 1 factorial for the one element. Or you could leave it out. It really doesn't make a difference. It's not going to blow your mind, and it's not going to make the answer incorrect. 3 factorial for the 3 green, 2 factorial for the 2 red. Now, most people will just go 3 and just account for the repeating elements and leave out the 1 factorial, which, again, it doesn't make a difference because it's 1 and you're multiplying it, so it's not gonna blow things up. Okay, so again, we get our 10 factorial. Okay, and then I go divided by 4 factorial is 24, and then 3 factorial is 6, and then 2 factorial is 2, and there we go, 12,600. So strangely enough, when I'm eating M&Ms, okay, and I only have 10 pack in one of those little itty bitty bags, even when there's a lot of repeats, there's still 12,600 ways to eat all the candy in that bag. It kind of blows your mind when you have a lot of elements. You can really have a lot of possible scenarios, okay? Now, this one's a little bit more interesting of one. And for some people who play a game and stuff like that, they're like, oh, I don't know if I agree with this. But either way, okay, this soccer season is over. The team won 5 games, lost 3, so won 5, lost 3, and tied 2. Okay, so they played 10 games. How many different ways could these outcomes have occurred? In other words, how many different orders of wins and losses and ties could there be? Now, for you, you're going to be like, well, all the games are different. They played against different teams, and the scores were different, and different people scored the game and during the game, and different people played in different positions, and blah, 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 blah. Yes, I understand that. But if we just view them as wins and losses, and that's it, how many different ways could we arrange these? Well, that means that basically this is arrangements of letters where we have 5 W's, 3 L's, and 2 T's. Obviously, it wouldn't make a logical word, but again, it's not about rearranging words. Okay, it's about bringing this back to a practical situation. And if you have identical outcomes, you want to see how they come about. Okay, it's like flipping a coin and getting heads or tails. They're identical outcomes. Okay, if you want to do them in order, then you just got a bunch of H's and a bunch of T's. Okay, so anyway, we've got 10 elements and 10 positions, right, because there's 10 games that were played. And so my number would be, and again, I know I have 10 elements and 10 positions, very repetitive. Okay, 10 factorial, treat them as if they're different, or 10p10. It's nice because you start sort of simply, and then you say, okay, let me just correct, and elaborate and make it more correct, or, I don't know, refine the situation. So you've got 5 factorials for the games that are won. We've got 2 factorial for the games that are tied, and 3 factorial for the games that are lost. Once again, 5 factorial for the wins, 3 factorial for the losses, and 2 factorial for the ties. Again, viewing them as W's and T's, and not games with different individual scores and things like that. Okay? I evaluate that. Again, it's going to be 10 factorial. Okay, and then we divide by 5 factorial, which is 120. Then we divide by 3 factorial, which is 6. And then we divide by 2 factorial, which is 2. And we end up with 2520. So even in that season, if you just view them as wins and losses and stuff, there's 2,520 different ways, or different seasons, with 5 W's, 3 L's, and 2 T's. Okay, if you view it that way. And so that's that little correction factor that's associated with that. Okay, now I want to include this, although it depends on the textbook. They do have some questions and focal points on this, and sometimes they don't. Okay, but again, this is the whole idea of removing variability. Okay, and in the new textbook, they actually have a section on this, and they have quite a few examples on removing variability, and it's a good idea. Some books don't focus on it. The old book doesn't. Okay, but it's a great idea. So how many ways can you arrange the letters in the word handout? Okay, so 1, 2, 3, 4, 5, 6, 7 elements. I'm arranging the letters, so there's going to be 7 positions. I'm not leaving any of them out. Okay, now, so that the vowels are still in the correct order. Okay, so in other words, the A is going to be first, the O is going to be second, and the U is going to be third. And that's a bit tricky. Okay, because, you can have an H and have an A-O-U. Make that look like an H, and then have an AOU, and then have, I don't know, an NDT, or you could have an H and have an an N, and then have an A, O, U, and then a D and a T. As long as you have the A, O, U together, but they don't have to be side by side. So you can have an H and an A, and an N and an O, and a D and a U and a T. Okay, but the A and the O and the U are in that order. What you can't have is, you can't have an A, U, O. You can't have an O, U, A. You can't have an O, A, U. You can't have a U, A, O. And you can't have a U, O, A. So you can have an A, O, U, which is cool, but you can't have that, can't have that, can't have that, can't have that, can't have that. So we're removing those possibilities. And if you notice, it's 3 elements, and there's 6 possibilities, but we're narrowing it down to 1. So the strategy is still the same, okay? If they need to stay in that AOU order, okay, and we've got 7 elements in 7 positions, okay, it's going to be 7p7, 7 elements in 7 positions, or 7 factorial. If you want to go quickly with that, that's cool. You've done enough of this work. You're allowed to jump past that if you want to, but I do recommend that you map that out, okay, or at least write that down. Now, there's a correction factor here, because we could have AOU, we could have AUO, and all those different situations, but we can't have any of these. These are now gone. So of those 6 possibilities, we only have 1. So what do? We divide by those 6 possibilities. Or, because there's 3 elements, we divide by 3 factorial. So it's almost like we treat those 3 as if they're identical elements, but they're not identical elements. What we're doing is we're losing, we're losing arrangements, not because the elements are identical, but we're losing arrangements because we can't arrange those. The same reason. Okay, because when the elements are identical, we can't have different arrangements. And if we're not allowed to arrange these, then we can't have different arrangements. So it's still the same thing. So it's still the 7 factorial, which I believe is 5040. Yeah, divided by 6, okay, or it might be 3 factorial. Okay, it ends up being 840 different ways, okay? So keeping that idea in mind, it's a little bit of a trickier situation. But again, it's all about removing or losing variability, okay? I'm not going to do this question for you. You have it in your notes, and the reason why I'm not going to do this question for you, although it's a good one, and I'll do it in another small little video for you that you'll be able to see in a second. The reason why I'm not going to do this is because it's actually a question from your textbook, okay? And it involves this idea. Okay, so there's a little explanation in here again for this. In this case, keeping the vowels in the same order removes the number of possible arrangements. Okay, so keeping them in that order removes all the other AOU, AUO, all those different arrangements. Okay, so only 1/6 of them are acceptable. 3 elements that are affected, dividing by 6. 6 is equal to 3 factorial, and again, it's not a coincidence. It's the same thing as having the A be AOU being AAA. Okay, losing the variability of number of possibilities from ordering A elements is effectively the same thing as treating those elements as identical. Like the word handout turns into the word HVNDVVT, where the A, the O, and the U actually end up being V's. As having identical elements does the same thing as fixing them in specific order. So, in summary, if you arrange n elements in n positions and A of those elements must remain in some specific order, then it's n factorial over A factorial. Same correction factor that we've been using. So whether there's identical elements or there's elements that need to stay in a specific order, it's that number of elements factorial that we divide by. Okay? All right. So there's going to be homework for you to do. It's actually here. I don't know why I printed it out, but it's here. Oh, this is the old textbook, so it's probably what we're going to be using if we're doing online learning. If not, then we may use a different textbook. That just means you have more examples. Okay? So the homework assignment will be a little bit different. Okay, but have a look at the homework assignment that's in your Google Classroom. It's not going to be the same as this one. It's going to be the stuff from this page. I forget the, oh, here it is. Here are the questions that you're going to do. Okay, so I don't know, focus right on that guy. Okay, number 2, 4 to 7, 10 and 11 to 14, and 16. 16 is the one that I'm actually going to take up in the next little itty bitty short video.